Let's be honest, solving systems of linear equations can feel like a total grind. You're juggling variables, rewriting equations, and one tiny slip can derail the whole thing. But what if there was a seriously smart shortcut? A method that just gets you straight to the answer? Well, in this explainer, we're going to dive into that exact tool.
You know that feeling, right? You're using substitution or elimination, you're halfway down the page, and then you get that sinking feeling that a tiny mistake way back at the beginning has thrown everything off. It's just a mess of paper, time, and tangled algebra.
But there is a better way, a method that's more like a clear step-by-step recipe, a way to get straight to the answer without all that messy rewriting.
And it's called Cramer's rule. It's this really elegant method that uses a concept from matrix algebra called determinants to solve these systems directly. Now that might sound complex, but I promise you the process is incredibly straightforward.
So, what in the world is a determinant? Well, think of a matrix as just an organized grid of numbers. A determinant is a single, unique value we can calculate from that grid. It basically unlocks key information about the system of equations, and it's the core ingredient that makes this whole recipe work.
And this is why it's a real game changer. As our source material puts it, this is a fantastic improvement over those traditional methods. It completely replaces all the guesswork and complicated algebraic steps with a simple, repeatable process.
Okay, so let's start with the most common scenario, a system with two equations and two variables, like x and y. I'm going to walk you through the recipe step by step.
The setup is just beautifully simple. Seriously, you just create three matrices. First, you have the main matrix, D, which is just the grid of coefficients from your variables. Easy enough. Then, to get the matrix dx, you just swap out the first column, the x coefficients, with the solution numbers. And you do the exact same thing for the second column to get dy. That's it. That's the entire setup. And here is where the magic happens. To find the value of x, you simply divide the determinant of dx by the determinant of d. And for y, it's the determinant of dy divided by the determinant of d. That's it. Two simple divisions give you the answer. No messy algebra, no fuss.
So that's how it works for a simple 2x2 system. But what about bigger problems? Well, the real beauty of Cramer's rule is how elegantly it scales up. The same core logic applies no matter how big the system gets.
For a system with three variables, x, y, and z, the formulas are pretty much identical. We just add a third ratio for z, using a new matrix, dz, where you replace the z column with the solutions. The recipe holds up perfectly. It's just wonderfully consistent.
And this is where the efficiency really shines. The source material points out that solving a 3x3 system with elimination can take over a full page of writing and rewriting. Cramer's rule just cuts right through all of that, dramatically speeding up the process and, maybe more importantly, reducing the chance for error. But there is one crucial exception we need to talk about. What happens if that main determinant, the one in the denominator of our fractions, turns out to be 0?
Just think about it for a second. We've got this neat little formula, but it's a fraction. So what's the number one rule of fractions we all learned back in grade school? You can't divide by 0.
Exactly. It's undefined. So if our main determinant, d, is 0, the rule as we know it kind of breaks down. But that doesn't mean the information is useless. Actually, it tells us something very specific about the system of equations itself. When that main determinant is 0, it's a huge signal that the system is unusual. It means one of two things is true. Either the lines are parallel and they never ever cross, meaning there's no solution, or the lines are actually the exact same line, right on top of each other, meaning there are infinite solutions. Cramer's rule helps us spot these special cases right away.
So this brings us to a really important idea. We've talked about Cramer's rule being faster, but its real power is that it's smarter. See, true efficiency isn't just about getting the answer quickly.
The source defines efficiency as minimizing the number of decisions you have to make. It's about having a clear, definite algorithm that you can follow every single time without having to stop and think, what should I do next?
So let's compare them directly. With elimination, you're constantly making these strategic choices. Which variable should I eliminate first? What number should I multiply by? It's messy and it opens the door for errors. Cramer's rule? It's purely systematic. It's one clear algorithm which minimizes those decision points and all those potential mistakes.
I absolutely love this quote from the source material because it just gets to the heart of the matter. A computer, or a student, is great at following a recipe.
It's not so great at making these strategic judgment calls in the middle of a complex problem. Cramer's rule is that perfect recipe.
So the crucial point is this. The genius of Cramer's rule isn't just that it's fast, it's that it is reliable. It provides a clear, unambiguous, and powerful recipe for finding a solution every single time you use it. It turns what could be a confusing puzzle into a simple calculation.
And that leaves us with a final thought to chew on. We've seen how a powerful algorithm can bring so much clarity to a math problem. So, where else in your life, whether it's at work, in a hobby, or even just planning out your day, could applying a clear, step-by-step recipe help you simplify something complex?